If you're dreaming of going to space anytime soon, you'll need a massive rocket to get there. But someone came up with a bold alternative. What if we could throw something so hard it reaches space? That's exactly the concept behind SpinLaunch, a startup that's taken on the challenge by building a sub-orbital accelerator, a proof-of-concept system designed to launch payloads into space. So, what exactly is this method they're pursuing? And more importantly, is it even possible? Let's find out in today's episode. You might not know this, but just 2 years ago, SpinLaunch's technology was considered the space industry's best-kept secret. The company stands out by taking a completely new approach to one of the oldest challenges in launching objects into space, the rocket equation. Since the dawn of the space industry, aerospace engineers have grappled with a frustrating paradox. The fuel required to launch a payload into space is itself a significant part of the weight that must be lifted. This creates a vicious cycle. More fuel is needed to carry the extra fuel, which is why traditional rockets end up being more than 90% fuel. The result? These massive rockets are essentially flying fuel tanks, leaving only a small fraction of their total mass for the actual payload. SpinLaunch has turned this entire paradigm on its head. Instead of relying on the conventional method of launching rockets loaded with enormous amounts of fuel, the company developed a revolutionary solution, maximizing acceleration for the payload right from the ground. They achieve this with a launch system that's essentially a vacuum centrifuge made up of an electric motor, a vacuum chamber, and an arm that spins incredibly fast. The operation is surprisingly straightforward. A small rocket is loaded onto the spinning arm, which accelerates it to an astonishing speed before launching it outward. By delivering such a powerful boost directly from the ground, SpinLaunch can drastically reduce the amount of traditional rocket fuel needed to send objects into space. The payload will pierce through Earth's dense atmosphere at hypersonic speeds, specifically at least 6 times the speed of sound, or an incredible 2.1 kilometers per second. According to the projected plan, the payload will reach an altitude of 60 kilometers using nothing but pure kinetic energy. Not a single drop of fuel is required during the initial phase. Once it hits this height, the mini-rocket will fire its engines to accelerate to orbital speeds of 27,600 kilometers per hour. Sounds pretty straightforward, right? Well, behind these impressive numbers lies a staggering engineering challenge, the tether system. To make this vision a reality, SpinLaunch needs to build an extraordinary load-bearing structure, the strongest cable ever created by humankind. With the machine's radius measuring around 50 meters, this tether must spin at 450 rotations per minute to achieve Mach 6. The aerodynamic shell, which houses both the payload and the rocket, will weigh up to 10 tons. But here's the kicker. It will generate forces up to 10,000 times its own weight due to the extreme acceleration. This means the tether's leading edge must withstand a tensile force equivalent to an astonishing 100 million kilograms. At this critical juncture, materials science steps into the spotlight. The strongest materials in terms of specific strength are typically fibers like carbon fiber, fiberglass, and various polymers. These are often used to create ultra-durable composite materials. In the end, carbon fiber reinforced plastic, CFRP, was chosen. This material boasts an incredibly high strength-to-weight ratio, making it the perfect candidate for the super-resilient tether. Fortunately, SpinLaunch didn't have to start from scratch when developing their massive tether. They drew inspiration and expertise from the wind turbine industry, specifically from the manufacturing of giant wind turbine blades, which also rely on advanced carbon composite materials. By adapting and refining engineering solutions from other industries, SpinLaunch significantly shortened their research and development timeline, a testament to how cross-industry innovation can accelerate groundbreaking technology. However, spinning an arm nearly 500 times per minute brings its own set of challenges. At such speeds, air friction generates an immense amount of heat, similar to the aerodynamic heating Starship experiences when re-entering Earth's atmosphere at supersonic speeds. To overcome these obstacles, SpinLaunch had to develop an incredibly bold engineering solution, a completely sealed vacuum chamber. Maintaining a near-perfect vacuum isn't just a technical hurdle, it's also a costly endeavor. Creating and sustaining such an environment demands significant resources and the expertise of some of the world's top specialists. In the US, for instance, there are only a handful of vacuum chambers designed for space applications, most of which are owned and operated by NASA. Private companies typically rely on these existing facilities rather than building their own, saving costs and resources while leveraging NASA's well-established infrastructure. Maintaining a functional vacuum chamber requires the combined expertise of physicists, material specialists, aerodynamic engineers, and system designers. I can imagine SpinLaunch faced significant challenges in building a working prototype of their launch system, but they overcame those hurdles, and the result is a massive circular launch platform. Now, we already know that SpinLaunch's method aims to minimize the use of rocket fuel. However, launching anything into space still requires energy. With SpinLaunch's approach, electricity takes center stage. Their launch system uses electric power to spin the tether at extremely high speeds, generating the kinetic energy needed to hurl objects into space. That said, the geographic locations of launch platforms pose a major challenge when it comes to power supply. As you might know, most satellite launch sites are built in remote areas, typically along coastlines or in deserts, far from populated regions. These areas often lack robust infrastructure and have limited access to reliable electricity, forcing operators to find creative solutions for energy supply. To tackle this issue, SpinLaunch has considered using regenerative braking systems, which would recover kinetic energy from the tether after a launch and convert it into electricity for reuse. It sounds like an ideal solution, but as of now, there's no indication that they've made any significant progress in this area. To get an object into orbit, achieving extremely high speeds is a non-negotiable requirement. Unlike traditional launch methods that rely on gradual thrust from rockets, SpinLaunch's approach demands that all the momentum be built up at the precise moment the object is released. Here's where the technical challenge lies. For most real-world payloads intended for space, accelerating to the required speed and punching through the atmosphere generates immense pressure and heat. These forces are so extreme that they could completely destroy the payload, reducing it to a blazing trail of debris. And one more thing, the total mass of the payload system is 11.2 tons, with a significant portion, several tons, dedicated solely to the carbon fiber aerodynamic shell. The actual payload capacity is just 200 kilograms, which is quite modest compared to traditional solutions. For comparison, Rocket Lab's Electron rocket, a more conventional satellite launch solution, can carry 300 kilograms of payload with a slightly higher total mass of 12.5 tons. This means Electron achieves a much better payload-to-total mass ratio than SpinLaunch. Looking objectively, SpinLaunch is facing incredibly serious technical and commercial challenges. Theoretically, their launch method is feasible, but success requires more than just proving technical viability. The reality for any satellite launch service provider goes far beyond technological achievements. To grow, they need to sell, and this is SpinLaunch's critical weakness. The company aims to cater to the small satellite launch market, but this segment is already saturated and fiercely competitive. SpinLaunch's potential customers currently have countless options, with SpaceX's Falcon 9 rideshare program widely regarded as the gold standard. The Falcon 9 rideshare service isn't just the most affordable option, it's also viewed as the safest and most reliable traditional choice. Satellite operators are understandably hesitant to entrust their valuable payloads to a launch system that is still new and unproven. Customers would have to invest significantly in hardening their payloads to withstand the extreme launch conditions of SpinLaunch. Protecting satellites from these stresses would require complex and costly technical solutions. In reality, for most satellite operators, the cost and risk of experimenting with an entirely new technology far outweigh the potential benefits. Safeguarding multi-million-dollar satellites during an unproven launch method is a highly risky business decision. I have to admit, SpinLaunch's model represents a groundbreaking shift in how we think about space exploration. Is it possible? Theoretically, yes. But can it survive in today's market? That's a tougher question. What do you think? Comment yes if you think SpinLaunch has a chance in the industry right now. In fact, there haven't been many updates from SpinLaunch about their system recently. If you're curious, I've covered an overview of their situation in a previous video. Feel free to check it out. That said, I can't help but feel that things haven't been going so well for SpinLaunch lately. Sure you don't miss any key updates on this thrilling journey. Make sure to subscribe to our channel. All right, that's it for today. Thanks for watching, and we'll see you next time.